Thank you very much for the introduction, and thank you very much to the organizer and to the scientific committee. I'm so grateful and honored to be here, and I hope this talk will be worth of this very important slot in the program. I would also like to thank Eugenia for her help in preparing the talk, and Francesco, which is my collaborator, because I felt very lucky to work with him on this on this paper, which is the derivator associated to a DG category. So, how I'm going to introduce it to you, I will first give you some motivation, which arise in derived categories, and then I will introduce the main definition, which are of course derivator, DG categories, and quasi-functors, which will be the main tool, which will allow us today to state the main result, together with a new notion of homotopy limits and colimits in DG category. And at the end, I would like to present what I believe is a nice application of the main result. But let's start. And for us today, K will be a field. We can define the derived category of modulus over K as the localization of chain complexes at quasi-isomorphisms. So, as in any category, we would like to compute limits and colimits. But here, since we have this localization, we look at homotopy limits and colimits. So we want to look at map from the diagram category to the derived category itself. But if you consider the derived category of an abelian category, in general, this is not a functor. So we have a problem here, and what are some ideas for a solution of this problem? The first idea is that instead of considering the diagram category, we can instead consider the derived category of the diagram category. And this leads to the notion of a derivator. The second idea is that we can still consider the same diagram category, but enriched over the derived category. This is not very precise, it's just an idea, and this leads to the DG categories. The third idea, I'm not going to introduce it, but has been widely introduced at this conference, and leads to the notion of infinity categories. So in the literature, we know how to pass from a DG category to a derivator, thanks to Rie, Groth, and Schulman, but this construction is quite technically complicated and hard to deal with. So, me and Francesco were wondering, does it exist a direct connection from DG categories to derivator? And so this is the question we're going to answer today, hopefully. So, what are derivators? So derivators are two functors from the category of small category to the category of not necessarily small category, which, given a small category I, associates a category Di, and whenever we have a morphism U from I to J, his image under the derivator is denoted by U upper star, and is called restriction. And here is called restriction because in the case where U is, for example, the inclusion functor, you can really think of it as a restriction. So, in order for this functor to be a derivator, it has to satisfy many very technical actions. So, I'm not going to introduce them today. But what is important for you to know is that this action requires, for any restriction, that the left and right adjoint of the restriction always exist. And these, even in this context, are called left and right extension. So, since this is very technical and formal, let's see an example. And the example which gives the best intuition, I believe, is the one of represented derivator. So, it's represented by a bicomplete category C, and it sends a small category I to the functor category from I to C. So the idea here is that we are really looking at I-shaped diagram in the category C. So this is what you can keep in mind to think about derivators. So if you think in this case, you take the restriction and you compute the left and right can extension, you recover the classic notion of the left and right can extension. And since it's bicomplete, you know that they always exist. So here we actually have a derivator. The second example is the one related to the derived category, which was the one we were interested in, and as I pronounced, sends a small category I to the derived category of the diagram category. And I would like to underline once more that this is actually different from the diagram category itself. So we remark this different by speaking about coherent diagrams and incoherent diagrams. So derivators are I-shaped coherent diagrams. Okay, so when we speak about derivator DG category, we say they are enhancements of the derived category. So in which sense derivators are an enhancement of the derived category? Which is more or less the same as asking, how do we recover the derived category when we have a derivator? So, if you take E, the terminal category, and you evaluate your derivator in E, what you get is what is called the underlying category. And if you do this in the second example, then you can see that you can recover our derived category. So, in this sense, derivators are an enhancement of the derived category. Okay, so, derivators, what about DG category? So, DG category are a category enriched over chain complexes. So, this is a simple definition. Let's also here see an example. So, this is a DG category where the I are the objects, and every different colors of the arrows are arrows in different degrees. So different colors are different degrees, and the degrees are denoted close to the arrows. So this is an easy picture, and it's interesting because it actually also represents an object in another derived in another DG category, which is the derived DG category of C, which is defined as the localization again at quasi-isomorphisms of the DG category of chain complexes of C. Why am I interested in this derived DG category? Because of another category, which is called A5, is a small category. And so A5, if I consider the functor from A5 to mod K, to modulus over K, I can also here define the derived category of this small category. And similarly, if I take the quotient over an ideal here, which is generated by the composition of every two consequent arrows, which means that the composition of every two consequent arrows vanish as per complex, then if I take the quotient, I can also similarly define this derived category. So, what it turns out to be is that here, if you define the differential of this red arrow to be the composition of the two black arrows, which they correspond to, if you take the zero cohomology of the derived DG category of C, you get back, you find the derived category of A5 over I. So in this sense, the G category enhances the derived category, because if you take the zero cohomology of a DG category, then you get back your derived category. Okay, so this is the same as I introduced for derivators, but what is interesting about this enhancement over chain complexes? Sorry, this enrichment over chain complexes. So, we have chain complexes, so we can do homotopy-Theorian chain complexes. But the homotopy-Theorian chain complexes, actually, this structure reflects also in DG category. And you might wonder, how? So, Tabuada gives us an answer. Tabuada gives us an answer by proving that DG category actually have a model structure whose weak equivalencies are given by quasi-equivalencies. So, what are quasi-equivalencies? These are just an analog of quasi-isomorphisms for DG categories, because they are quasi-isomorphisms on chain maps, and then when you take the zero cohomology of the functor, you ask for it to be essentially surjective on objects. So, for example, these two are, if you take this as a DG category concentrated in degree 0, these two are quasi-equivalent. Okay, so we have a model structure, so naturally you can define the homotopy category of DG category, which is the localization at these quasi-equivalencies. And this is actually the setting where we want to work in. And as also Martina underlined in her talk, when we want to work with well-defined objects and functor in this homotopical setting, and in derivators we actually want to define a diagram category of, we need well-defined functors. What we can look at is actually the internal home. What we can consider to look at is the internal home. So, is the homotopy category, does the homotopy category have an internal home? The answer is yes, and it's given by by Toen, which prove that quasi-functors provide the internal home in this homotopy category. So, what are quasi-functors? Let me first define what a DG bimodule is for two DG categories A and B. These are just DG functors from the tensor product of A and B to the DG category of chain complexes. So due to this definition, even here, we can define his derived category, which is again the localization at quasi-isomorphisms. Now, a quasi-functor is an element in this derived category, which is right quasi-representable. So this condition requires for any object A in A that there exists an object phi f of A in B such that the quasi-functor evaluated in A is quasi-isomorphic to the functor which is represented by phi f of A in B. So basically a quasi-functor is an element in the derived category with this weak notion of representability. So I know this is quite technical and formal as a definition. What you can keep in mind is that quasi-functors are the good notion of functors when you want to work in the G category up to weak equivalencies, and in this case, quasi-equivalencies. So this is what you can keep in mind. Okay, for the rest of my talk, I'm going to denote the category of quasi-functor by R home A and B. So, now we have derivator, we have the G category, we have a good notion of functors. So, we can try to make a claim and try to define the derivator associated to the G category. And why not sending a small category I to the quasi-functor from the k-linearization of I, because it has to be a DG category, and it becomes so that it becomes a DG category concentrated in degree 0, and the DG category A. So this should be the derivator associated to the DG category A. Let's see if this is actually a good claim. So what we wanted to enhance the derived category. So we wanted the underlying category of this derivator. We wanted the underlying category of this derivator should be the zero homology of our DG category. But if you look at our claim, this only happens if we also take the zero homology of our quasi-functor. So now this is a way better claim, and we might think how the restriction is defined in this case, and you get a good definition just with the natural one that you might give, which is by the precomposition with the morphism U. What do we miss in this picture are the left and right Kahn extensions. So, how do we define them? They are particularly limits and colimits. So, first we need a theory of homotopy limits and colimits in the G category. Let's look at it. And the idea, so these are the left and right Kahn extension that we miss. So the idea here is that we start by looking at what happens in normal categories. So if you need to compute the limit of f, you compose it with the Yoneda functor, then you first define it as a functor, and then you ask for representability. But I want to work in the G categories. So let's make some change. Let's k-linearize I. Let's substitute A with the G category A. Let's substitute sets with the G category of chain complexes over K. And then I need one more data, which is called weight, and is a functor from Ki to the DG category of chain complexes over K. And I substitute this weight here where I had before the constant diagram functor. What I recover by making this substitution is the notion of weighted limits, which is actually the good notion of limits when we work with a rich category. So, great. Now we don't only work with the G category, but we want to work in the G category up to quasi-equivalencies. So we want to take care of the homotopical structure. And the idea is that we can extend this further to a notion of weighted homotopy limits, which also care about this. So let's take a quasi-functor, and the weight, in principle, is also a quasi-functor, but due to this codomain, you can easily see that he can just be defined and make things much easier, just as a DG module in the derived category of I. So again, we can think of, if we want to extend what would happen before, we can take the weighted homotopy limit. But how do we care about the homotopy theory? So, as when we define the right functor, this is not a surprise, we can take just a resolution of the weight. So, this is the same idea as when we define the right functor, and this is enough for this limit to take care of the homotopy theory in the DG category. And again here, we ask, so this was the functor, and we ask for representability, but in the derived category. So this is a weak representability. And so this is the notion of weight homotopy limits in DG categories. Nice. So with this ingredient, we now, and together with our claim for the derivator, we can now see if we can define the Kahn extensions. Okay, Kahn extensions are particularly limits and limits over slice category. So what's the idea now is that with this notion of homotopy limits and colimits, I need to put inside the structure of the slice category. And where I can put it? In the weight. How do I encode this? This is just the idea behind, but how do I encode the slice category, the structure of the slice category in the weight? By defining, so for any small objects j and j, my weight will be the functor which is precomposed on the right with u, and where I fix the first coordinate to be j. And then at this point I define the right Kahn extension of f along u, evaluated in a and j, as the homotopy limit of f of a, where the weight is wj. And dually, of course, I can define the left Kahn extension. So now I have everything, so I can give you the main theorem, and the main result is that if given A a DG category, if A has all weighted homotopy limits and colimits, then our claim for the derivator, which was the A, is actually a derivator. So this was actually the answer to my question at the beginning when I spoke about the motivation. But I would like to tell you more about this theorem, and in particular to present what I believe is a nice application. So let's go back to our derived category of A5 over I. If we want to study an enhancement of this category in the derivator, it is possible to prove that it can be a derivator which is described by such a poset. Okay, but this poset and this enhancement is not very natural to find. It's not really straightforward. So what is more straightforward when you work with the right categories to do is taking instead the DG enhancement. And we already saw what's the DG enhancement of this right category, which was the right DG category of C. Now that I have my theorem, I can actually apply the theorem to this particular DG category, and I will get a derivator. So this is a joint work in progress for a reason. One of the reasons is that I still don't have all the details of this equivalence, but I'm confident in this, that this derivator that you get via the theorem is actually equivalent to a derivator which is described by a poset which looks as a pyramid. So the colors here are not random, but they are in correspondence with the arrow in the DG category. And also, as you can imagine, here we are working with A5, but I can easily extend everything which is in the slide to AN. If I do this, then this pyramid will be much higher, and it will have n-2 floors, layers. So it will not be a very pleasant poset to deal with and to work with also. So it will not be an easy enhancement to work with. But at level of derivators, what it turns out to be is that this enhancement, this derivator is actually equivalent to the one I introduced first. Okay, what does this diagram says? So, the colorful arrows are what we call in homotopy theory hygromotopes. Hygromotopes are what encodes all the data that you need in order to have well-defined functor and objects up to homotopy. So they might be a lot. You need a lot of data. I'm not sure officially, but maybe it's just my my idea. But like in infinity categories, there's an infinite. It's not random, because you might have infinite amount of this data. So basically, the pyramid will be higher because you have a lot of data in what is the more natural enhancement of this derived category. And then now, thanks to this theorem, because when I first found this announcement, I didn't know why actually we can actually compress and encode all the hygromotopes in only one arrow between the yellow objects. So now that I have this theorem, I actually know why and how these homotopes work and how we can actually compress all the hygromotopes in only one arrow between two objects, basically. And they can reduce the problem. I can reduce, let's say, I can work with such an easier enhancement and I should not take care of all these higher arrows. Okay, so I guess this is the end of my talk. Thank you very much for the attention, and here are some references.
Question.
Thank you for the nice talk. I was wondering, so my understanding is that the problem consists in the observation that the limit functor usually is not a right Coulomb functor, for instance, but it is well known, there have been some work as that shows that the enriched limit functor is right Coulomb usually.
Is right?
Right Coulomb.
Okay.
So I was wondering, so this is work by Gambino, for instance, for the projective injective model structure, and Reed for the Reedy model structures. And I was wondering whether this is particular to the GG category, or does your work fit into a more general framework for homotopy limits as a weighted limit in an enriched setting?
What we did was on purpose for DG category, was precisely in the setting of DG category. We didn't look at limits in model categories, let's say. I mean, I'm also the way we constructed everything, I think it really stays in DG category. But I cannot say this is not related to what you just said. Probably from what you described, it might, I mean, there could be a connection, of course, and yeah, so I mean, I believe this can be put in a wider context where you speak about limits and homotopy limits and colimits in enriched categories, let's say. Also, maybe the talk of Giovanni, probably, Leoncini, probably. Yeah. Yes, so you're right. I think a bit, I don't know. I mean, we were thinking about it, let's say.
Fosco, you had a question.
Yeah, the definition of derivative is engineered not only to guarantee the existence of left and right hand statements, but to be able to compute them point-wise. So,
yes.
It's not really clear if this notion of derivative seems like a little generalization that now allows you to compute weighted colimits without the guarantee that they can be computed point-wise. Or I misunderstood.
I mean, these are like defined as functor. If you evaluate the functor in the point, I guess you get what you want, right?
CAN extensions are not limits or colimits over comma categories. These are pointwise CAN extensions. And you want to compute those. You want to be able to reduce.
I mean, this is an action, right? This is an action about the CAN extension that you have, and you can prove the action with this notion of the CAN extension.
So your weighted colimits now can be computed pointwise, like they can be reduced to conical colimits, or not?
I mean, I don't exactly know what you mean.
Oh, okay.
Conical colimits? Yeah, I think so.
Go ahead.
I think actually she looks rather at enriched limits and colimits, and weighted. I'm sorry, weighted, and it reminds me very much. There is in simplicial or multiple theory. So when you have a simplicial diagram or even a strict diagram in simplicial sets, then there are formula to compute the homotopy colimit and the homotopy limit of such a diagram by using the so-called replacement schemes of Busekan. And the formula and they use you can also express it at weighted limits and colimits, and the formula for your right the right thing is precisely the replacement scheme of Busekan. This is precisely the same formula.
Okay.
So I don't think that this is a coincidence.
No, thanks. I have a lack of knowledge about schemes, probably. But thank you very much for your.
Richard, you have a question?
So one thing that comes to mind. Thanks for the talk. Very nice. So, do you think about replacing the things that index your D by not just categories but also DG categories? So then, rather than just looking at linearizations here, rather than having KJ, you've just got a general DG category, J.
No, we didn't think of it actually. No. I don't know what you would get in this very moment. If you, no, we didn't think of it because we didn't need it in principle. So yeah, maybe it would be interesting. It would be interesting to see. But
One final question. Thanks very much for the talk. This is more of a naive question because I'm not necessarily like in the specific field, but you mentioned that your equivalence demands all weighted homotopy limits and co-limits to exist, like your main theorem. But this, you are only using specific weights for these right and left conic extensions, as I understand. So could you get like a sort of
so actually this is a bit farther as a request, because the actual theorem says that A should be a pretriangulated DG category. So, which means that A as in, strictly speaking, as cons and shifts, well, defined point degree-wise. So then you can prove that the existence of weighted homotopy limits and colimits implies this condition for a DG category to be pretriangulated, which is of point first.
Cool.
I don't know if I answered.
I think so, yeah.
Yeah.
Let's have the speaker again.